So here's a little demonstration of the generator effect. What we have here is a turntable, and we're moving that turntable using mechanical energy from an external source. Could be something that's actually turning it, could be a gerbil in a cage, it could be water power, it could be turbines driven by coal or by fusion fission reactions. And of course we move that loop of wire inside a permanent magnetic field. At the top we have a north, at the bottom we have a south. And if we look at this very carefully, we can see that the third left-hand rule applies, and of course Lenz's law also applies. When you move that wire within a permanent magnetic field, the electrons in the wire will experience a force. The direction of the force is determined by their motion within the magnetic field. And Lenz's law says that whatever motion they undergo, the magnetic field that they produce as they move will oppose that motion. And so we get a force that pushes the electrons. In this case, the red arrows here are indicating conventional current. So if we look at the electrons are being pushed to the back, and the electrons here are being pushed towards the front. So we get a loop that goes, in this case, the way I'm looking at it from this angle, it goes counterclockwise. And the electrons come back to the pickups, the brushes, and then they go into a voltmeter. And the voltmeter, of course, you can see that the voltmeter shows a negative current at some point. That negative just means it's moving in a certain direction. And then half a turn later, they're moving in the opposite direction. Notice the direction of the current indicated. The conventional current is left, now it's right, and then it's left. And it's these moving loops within the magnetic fields that generates much of the power that we enjoy on all of our devices. So what we see here is a generation of a current, and because we don't have a commutator, what we have is two brushes. The two brushes pick up the current during part of this rotation. The current goes in one direction, and during the second half of the rotation the current switches direction, and this occurs twice every rotation, and it gives us a frequency of oscillation. They call this oscillating current, or they call it alternating current, because the direction of the current alternates once every half cycle. And of course the electricity that we commonly use in North America is 60 cycle or 60 hertz, and it's generated. The first decision to do that was made when they built Niagara Falls, and they decided, how are we going to generate the power? Are we going to go with direct current, or are we going to go with alternating? They chose to go with alternating current. Now you could have, and many countries in Europe have gone with direct current, so they need a commutator. So here we just have two brushes. With a commutator, that is a split ring commutator, like we saw in the generator, in the motor effect, we saw that with a commutator, a split ring, the current changes direction inside the loop, but it doesn't change direction outside the loop because the split ring commutator takes care of that change. And so we always get a constant current in the same direction. Now when there's a split, there's a momentary loss of current. But if this commutator is spinning very, very fastly, like it would do in most generators, you're not going to notice that minuscule microsecond or nanosecond of time where there's no current. All right, and of course even if we speed this up, you'll see that at 12 rotations a minute there's a lot less time that it's actually sitting at zero. And if we speed it up to 20,000 rotations per minute, then we won't even notice that change at all. It'd be just a flickering that would be unnoticed.